Hello, sir. हेलो सर, आपकी वॉइस नहीं आ रही है।
Okay, 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 okay.
अब आया सर, अब आया।
Okay. So, okay. So, mic off था by chance. Okay, कोई बात नहीं. So, here we discuss about a Lagrangian algorithm for equality constants, and you have already studied the Lagrangian condition and KKT condition for equality constants and equality and inequality constant respectively. Okay, so here we discuss here the Lagrangian algorithm. In this case, you have any problem which is a this is a minimize any function, and that is your objective function, and subject to the constants, and there are equality constants, and there are suppose a key number of equality constants. So here this Rn, this H is mapping from Rn to Rq. Okay, so this means your X Rn to Rq. Okay, so here the Lagrangian function you have studied what is a Lagrangian function for any equality constants problem. So for every problem is you know that what is Lagrangian function, and that Lagrangian function is denoted by small l, okay, and that is uh, l x lambda, and you know that this equals to the objective function, and plus there are Lagrangian multiplier, that is lambda transpose hx. Okay, so this is your Lagrangian function, and here we assume that our objective function and our all equality function are second order continuous function. Okay, so we assume that these two are means your objective function and all equality constants are belonging to these are element of C2. Okay, so these are element of C2, as well as because you know that in your second order differentiability we have sufficient condition for what is the sufficient condition for this Lagrangian condition. So you this objective function and also equality function belongs to C2. Okay. So as usual in your Lagrangian method. Okay. So this is as usual, and we denote what is Hessian, and this Hessian of Lagrangian is denoted by capital L. This of Lagrangian, and that is capital L x lambda, and you know that what is the Hessian matrix. Okay, so now here we have discussed about what is the Lagrangian method. हमें नहीं देखना, हमें Lagrangian algorithm. In this iteration method for this type of problem, and if we try to solve that type of problem by using the iteration method, so here the what is the Lagrangian algorithm? So the Lagrangian algorithm for this problem is given by next iterative point is xk plus 1, okay, and that equals to your initial or previous point, okay, that is your xk minus alpha k, and here we take the gradient of our, because in you know that what is your in gradient method, your next iteration point is xk minus, and that is alpha k of the gradient you have to find for local minimizer. So that's why in the direction of that alpha, and here we're taking the gradient of your objective function. But here we not didn't take here objective function. Here we take the Lagrangian, because the Lagrangian function of this problem is defined by this form. Okay, so that's why we take the Lagrangian of this L. Okay, gradient of this Lagrangian function. Okay, so here the gradient of this Lagrangian function is this thing. So if we take in the gradient of that, the gradient of this plus gradient of that. Okay, so we write here this is gradient of objective function at the point that is xk, okay, and plus the derivative of u is hx, which is the gradient derivative of your h at point k with lambda transpose. So this is a lambda at the value the kth iteration. Okay, so we take the lambda k. Okay. So now, what is the value of this lambda k? So for that, the lambda k plus 1, by using that formula, this is obtained by this lambda k plus beta k h of xk. From this formula, you obtain your lambda k. Okay, and here you're putting there this value. So now in this step, you can find the next. First of all, your iteration point is x0. Then you're putting x0 here, x0. Okay, and then for next one, you find out what is the value of x1. For x1, this value here, and you're putting here x lambda 0 here. Okay, and for next one, you have to obtain from the value of lambda 1 from this relation and putting back in that, and you can find the next point. Okay, and similarly, you can find iteration next, second iteration, third iteration, and so on. Okay, so here, here we use only the gradient term here. This is the only gradient term here. So because only the gradient is used, the method is also called the first order Lagrangian algorithm. Lagrangian algorithm. Okay, and for the value of this x and lambda, so you have to find what is the optimum one, that is x star and lambda star, and that is satisfies your Lagrangian condition. So for the Lagrangian algorithm, for updating this xk and corresponding lambda k, that the pair is x star lambda star, that is your optimum one. This is a fixed point if and only if, this means fixed point, this is your optimum solution, if and only if it satisfies the Lagrangian condition. Okay, and you know that what is Lagrangian condition and what is KKT condition. Okay, so for that condition you have to satisfy, and then you take that pair is your optimum solution. Okay. Similarly, this is basically a simple algorithm for Lagrangian algorithm where there is only the equality constants are given. Okay. If any problem, if there are inequality and equality constants or simply inequality constants are given, that type of problem we have to solve by using KKT condition. Okay, and KKT condition you have already studied in some previous lecture. Okay, so in next page we here define here Lagrangian algorithm for inequality constants. So next page, so Lagrangian algorithm for inequality constraint, and here suppose there are some m number of inequality constants. So if we consider the following optimization, problem with inequality constants, and suppose you have to minimize our objective function, that is f naught x, and subject to constants, and suppose there are m number of equality constants. So here the function, that is g, is mapping from Rn to Rm. So the Lagrangian function for this problem the Lagrangian function for this problem is given by x lambda, and that is a function of objective function, and plus here we take mu because mu is your KKT multiplier. Okay, so that is gx. In the similar manner, in you take a lambda. So here, if there are only inequality constants, so you here write mu t. If there are some number of hx component are there, we have to adding here lambda and mu both. Okay. So here there are no equality constant. That's why here there is no component of lambda here. So that's why we take the only inequality constant problem. So that's why this Lagrangian function is written like in that manner. Okay. And here, as usual, you take here your objective function and of course inequality function, that both are your C2. Okay. So this objective function and g, this is belongs to C2 as usual. Okay. As usual. So now we denote Hessian matrix of the Lagrangian function Lagrangian by suppose L here x and mu. Okay, so now the Lagrangian algorithm Lagrangian algorithm for this problem is given by formula, and that formula is very simple as in previous case, that is Lagrangian algorithm for equality constant. So that's why we write here only replace the lambda term by mu. Okay, and same formula we use here. So the gradient of f naught xk plus derivative of g at point xk, and here we take transpose here. Okay, because you multiply this to this here, that's why we take here this transpose of your k. Okay, so now what is the value of uk plus 1? This is equals to uk plus this beta k g of xk. From this formula, this formula is very similar to the previous one, that is Lagrangian algorithm for equality constant. Okay, so here you know that this Lagrangian algorithm for updating this xk and mu k, and that there is x star mu star, and that is your fixed if and only if that satisfies your KKT condition. So in similar manner, you write here for the Lagrangian algorithm for dating these points next iteration. So the pair, and that pair is x star mu star, that is the mu star is a fixed point if and only if it satisfies the KKT condition. Okay. So basically there are two algorithms, and that is also in same manner of your gradient approach. Here your xk minus of alpha k, and this is your the values. Okay, and how can you find this alpha k and beta k and those values? Okay, so for that we will next. Uh, okay, so in next class we will explore that is I think we we will send the notes of your solve problem of that in your WhatsApp group. Okay. So now our these two topics, and then next one is the last topic, that is your penalty method. Okay. In next page, this is very simple formula, and the problem of any problem which is based on that formula. We will explore that either in next class, or we will send you notes, because if in any one problem if we try to solve, so this take much more time, about 45 to 50 minutes. Okay, so that's why we doesn't take any problem from these two sections. Okay. So today I will only explore what are the ideas, or what is the algorithm for the different methods. Okay. So now the last topic is your penalty method of your syllabus, and then we will move to the next next week. We will move to our one portion which is already I have left, that is linear optimization, in which we will cover your LPP, simplex, and game theory, and whatever the problem which is basically belonging to your linear programming problem. Okay, so now here we take the last method, that is the penalty method, and we will try to solve a problem which is basically based on that penalty method. And also the next graduate conjugate gradient algorithm, and we will also solve one problem from that algorithm also. Okay, so now we will explore two methods, and we will take two problems and try to solve that. Okay. And next week we will explore which is the portion I have left in your syllabus. Okay. So here this is the penalty method, and what is the penalty function, and then we define what is penalty methods. Okay. So basically in penalty methods, so we define what is the penalty function, and basically the role of penalty function is to penalize that points that are outside our the feasible set. Okay. So here, if we consider the general problem, we consider a general problem. That is, general problem means that problem in which both equality constants and inequality constants, and okay, so and that problem is your also belongs to your convex optimization problem. Okay, so any convex optimization problem, if we consider the general form, the general constant optimization problem, and that problem is either maximize or minimize, so we should reduce that, transform that problem to the minimization problem. Okay, so here the minimize of that is subject to the constants, either equality constant or inequality constants or both. So then we are able to find what is the your feasible region. So that in that case, subject this x belongs to several domain feasible region, that is your omega. Okay. If this means if we try to find if it's subject to the constant that equals to this thing. Okay. So here we approximate basically this is your problem which contain some constant here. Constant here either inequality or inequality or both type of. Okay, so this means your problem minimize something subject to certain constants are given. Okay, so here we have to approximate that objective with and reduce this problem, which is a problem of constant optimization problem, to unconstant optimization problem. So here we approximate the constant optimization problem ever by unconstant optimization problem. And then you solve that problem by using unconstant optimization technique. And you have already known that there are several techniques to find the minimization of any optimization problem or that are unconstant optimization problem. Okay, so how we can reduce this problem, constant problem to unconstant problem by using this is minimize. Your objective function is this thing, and here we introduce some gamma, okay, some gamma, and that is the penalty function x. Okay, so what is here gamma? So here basically gamma is your any positive constant. So your gamma is belonging to r, and this is positive constant and called that gamma is said to be penalty parameter. Okay, and what is your p? Your p is a function from your n variable to r real valued function. And this is a given function, and that function is called penalty function, and it's called penalty function. What is penalty function? So if we try to define that penalty function, so here any function, if we denoted that function is suppose p, and that is mapping from Rn to R, this is called a penalty function. It's called penalty function. For the constant problem, constant optimization problem, if it satisfies above, if it satisfies the following three conditions. The following first condition is your function p, the penalty function is continuous. So this function must be continuous. Second, your px, it is always greater or equals to 0 for all x that belongs to Rn. Okay. So you have to take in that type of function which is always either 0 or equals to 0 or greater than 0. When this equals to 0, when this x is belonging to your feasible region, because this x is belonging to whole Rn, in that Rn, this function, penalty function, is either 0 or greater than 0. And when this is 0, this third condition is this px that equals to 0, if and only if your x is belonging to this physical region, or x is physical, x is visible, that is x is belonging to this constant. Okay, so here clearly for the unconstant problem, that is defined above, to be a good approximation with the original problem, if we take the penalty function, if within that penalty function is appropriate, then that reduced form unconstant problem is very much close to that unconstant problem. So here we write here the penalty function. This penalty function, if we denoted by that function is suppose p, okay, that must be chosen appropriately. Okay. So here basically the role of penalty function is to penalize that points that are outside the physical set. Okay. So this is simple definition of a penalty function and how can we reduce our unconstant problem to constant one by using that. Okay, so here in next page, we illustrate how we choose penalty function. Okay, so one condition is if there are some inequality constants are given, suppose that there are suppose gx is less or equal to 0. So there are suppose inequality constants are given, so g1, g2, g3 up to gn. Okay, so we take the summation of that. So there is one possibility of your penalty function. Okay, but if we adding that nth or m number of equality or equality constant function, and if we take that what is the your new function that is a p, and that p is the summation of all the equality and equality constant sum of that. Okay, so that function j is may or may not be a differentiable function, and for optimization problem we have to the first order necessary condition is that the derivative at any point, that point is your optimum one. So the derivative should be 0. So this means your the penalty function, because we reduce that problem into this new problem, that is the minimize of that. Okay, and here we define the penalty function. And if we that function is, if we have to find that function is your minimization problem, for the first order necessary condition is that your first order derivative is 0 at that optimum one. Okay, so at that optimum value, that x equals to x star, this equals to 0 1. So that means the first order derivative should exist for this function. So here this is f naught is no doubt, because this is the element of c2 here. This f naught is equal to c2 here. So here this p should be differentiable function. So if we adding, there are suppose m number of your equality constants or equality constant functions. So there may or may not be that p is your differentiable one. Okay. So in that case, if there is a problem, then one scientist that name is basically there are two scientists. One is Beltrami and second one is Torrent. That two scientists made another form of penalty function, that is the squaring of each g1, g2, g3 up to gn, and then sum them. Okay, so in that sense, that function rho p is always differentiable. Okay, so now in next page we uh, write those things which have all just said here. Okay, so in next page, so to illustrate, how we choose penalty functions. How we choose penalty functions. So if we consider uh, a constant optimization problem, the form That form is minimize objective function subject to the constraints uh, di of x that is less or equals to 0. And here I is suppose there are n number of body constants. Okay, and what is the nature of your objective function, that is f naught. This is from R to R and R into R, and the GI suppose that type of function. Okay, and here I is varies from 1 to n. Okay, so now if this type of function here, so here considering only inequality constant is not respected. Okay, so here considering only inequality constant is not, either we take this is a because this is n, because we take this is gi, we take there are m number of m number of people. Okay, is not respected because and equality constants and equality constant of the form. Suppose if equality constants are suppose hx equals to 0, if we take that hx equals to 0, so this is basically equivalent to the equivalent to the inequality constant like inequality constant. Uh, we write here if anyone that equality constants are suppose of type something equals to something. Okay, so hx equals to 0 type of function. Okay, so if this can be written as an inequality form, that is we take this hx square is less or equals to 0. So these two conditions are equivalent, so we should replace that equality by inequality one. Okay, so therefore all constants are of type inequality conditions. Okay, so for the constants above, for the constants uh, problem constant problem is defined as ever. So it is natural that the penalty function be defined in terms of constant function, that is g1, g2 to gm. So a possible price for p, possible price for this penalty function p is we take here one possible form is if we take in this I is varies from 1 to there are m number of equality constants. So should write here gi plus of x. Okay, so what is gi plus here? So where, because we have to given here only gi function given g2 g3 up to gm, we take here the sum of all gi plus. So what is gi plus? So gi plus is for any function which has either, we take which one is maximum value of uh, the maximum of either 0 or that gi function. Okay, so this means you have to write here that value is 0 when your function is good, either 0 or negative 1. Okay, and here your function take as it is if your function is positive in that domain. So this means this is strictly greater than 0. Okay, so because we have to choose our penalty function is always positive one, that's why we take that is gi plus value. Okay, so in those interval that is so negative, so we assign that value is 0. Okay, and then we have to take what is the gi plus is the maximum of in both two. So this means you can say that gi plus means we have taken only that portion, that interval in which your function, your quality constant is strictly greater than 0. Okay, so that means we take only that point. Okay, so here if any point, if for that reason is also for 0, so in that case your function is in that case 0, and that is also 0 for all domain here. So that's why you take your gi plus is your 0. So now if we here we use, here we refer to this penalty function as the absolute value penalty function. Absolute value penalty function. Okay, so if we take an example and try to find what is the penalty function for that problem. Okay, so either we take not any of mentioned problem. So if we take suppose G1 and G2 here, okay, and we have to find out what is G1 plus and what is G2 plus, and then what is the PX. So PX is G1 plus and G2 plus. This is the penalty function. Okay, so now in next page, if we suppose that our G1 and suppose G2, these two are function from R to R, and this be defined by suppose the G1 is x minus 2 and G2 is the minus of x plus 1 cube. Okay, so these two are inequality constant. Okay, in that case, the feasible set defined by feasible set is defined by uh, collection of all x that belongs to R, such that so G1x is less or equal to 0 because this is subject to the constants, and here G2x is also less or equal to 0. Okay, so this is simply, if we try to find what is the reason. So this is simply the interval, simply the feasible set is you have to find the real number R, that is minus 1 and 2. Okay, so this is your feasible reason that satisfies both conditions. Okay, so in this example, we have G1 plus, and that is equals to maximum of 0 and our G1 function. Okay, and what is your 0? 0 means when x is negative 1. So this means when gx is negative, g1 1 is negative. When this x is either equals to 0 or less or equals to 0, in that case, this is negative, either negative or equals to 0. In that case, this is assigned as 0. And when this is strictly greater than, when all value of x is greater than 2, so this value is your x minus 2 if your x is greater than 2. Okay. Similarly, for if we try to find what is the value of g2 plus, g2 plus is maximum of 0 and g2x. Okay, so this means when we 0, when this value is negative 1. Negative 1 means if your x is greater or equals to minus 1. So if in that case, if this value is positive 1 and then this negative sign. That's why this value is negative. Okay. If we take x equals to minus 1, this value is 0. So for x is greater than minus 1 and 0, that value is 0. And if x is less than 1, this value is negative, and negative cube is negative, negative will be positive. In that sense, this value is x plus 1 cube when x is greater than, oh, less than. X is less than minus 1. If x is less than minus 1. So this is your g1 plus and g2 plus. So this means what is the penalty function? The penalty function is g1 plus and the summation of g2 plus x. Okay, because you know that your penalty function is defined by summation over I equals to 1 to here n or the 2. This is gi plus x. So that's why you're using that formula. Okay, so here is 2. Okay, so now if we try to combine this g1 plus and g2 plus, so your function is px is defined like this value is x minus 2. X minus 2 if our x is greater than 2, because real 9, this is your 0, this is minus 1, and this is 2. Okay, so here this x is greater than 2. This means you have your function defined by this thing. Okay, and here when x is less or equals to 2 and x is greater than minus 1, in that interval your function is 0 here, and here x minus 2. When x is less than minus 2, this function is defined by minus x plus 1 cube in this interval. Okay, so now you can define your penalty function by adding these two. If you're adding these two, so this function is 0 if we take the value of x in this interval, and that interval is minus 1 to 2. Okay, and here x plus 1 cube if x is less than minus 1. And if we try to plot this graph of the px, so the graph of that px is, so this is a 0, this point is 1, this point is 2, point is 3, and so on. So this point is minus 1, and here it's 2. Okay, so from minus 1 to 2, this value is 0 here. Minus 2, minus 1 to 2, this function value is 0. Okay, that's why you take this value is 0. Okay, and then after 2, this is straight line, and that straight line is like that. This function is your d1 plus x. Okay, and now uh, here, and after that, your function is minus of that. This function is defined like this thing. Okay, so this is minus of x plus 1 cube. Okay, and that is your g2 plus x. Okay, and here this is x minus 2. So this is your penalty function. This function is is your penalty function. Okay, so the absolute value penalty function, and that penalty function may not be differentiable at x, where this gix equals to 0, gix equals to 0. So here p is may not be differentiable at -1 point, and that point is 2. Okay, so therefore in such cases we cannot use the technique for the optimization that involves the derivative. Okay, so अगर आपने penalty function लिया, that is the sum of that. Okay, और अगर इसमें आपको penalty function है, अगर वो everywhere differentiable नहीं है, तो आप उसमें ऐसी methods आप नहीं लगा सकते जहाँ पे आपको क्या करते हैं कि डेरिवेटिव इन्वॉल्व है उन दैट मेथड में, ग्रेडियंट इन्वॉल्व है या फिर हमारे डेरिवेटिव इन्वॉल्व है, तो वो मेथड हम वहाँ पे यूज नहीं कर पाएंगे. दैट्स व्हाई ओके, so we can write here the absolute value penalty function may not be differentiable okay, at points, that is x, where this gix that equals to 0. Okay, so therefore in such cases, therefore in such cases we cannot use techniques for optimization that involves derivatives. Okay, तो हम ये नहीं कर पाएंगे. So there are another form that is your guarantee that your penalty function is differentiable. Okay, so that is your current Beltrami penalty function. Okay, so this means okay. So next page. A form of penalty function that guaranteed to be differentiable is current Beltrami penalty function. Okay, and that function is given by that penalty function, and this is given by that ex. This is the summation of I equals to whatever you take and value, and this is a gi plus of x will be squaring and then adding. Okay, this summation of that square function. Okay. So this guarantees your penalty function. In that case, your penalty function must be differentiable, and then your objective function is f naught x plus gamma times of px, and that function is your differentiable function. And then you can use your any techniques of your optimization that involves the derivative. Okay, so now we take example, and suppose we have consider the problem, and that problem is minimize those quadratic function. So this is a 2 of x and subject to the constant, and that constant is norm of this unit circle 30%. Okay, and what is q here? So your q is, you know that this is a symmetric matrix. This q equals to q transpose, and this is 0. That's the definite. Okay, so now if we using the penalty function, so problem example is that uh, using the penalty function, that is px, that equals to, so gx is x square minus 1 equals to 0 here. So we take norm of this minus 1 and then square. Okay, so the penalty function is, and the penalty parameter is gamma. Okay, so you have to write down, problem is you have to write down an constant optimization problem whose solution, that is x with parameter gamma, approximate the solution to this problem, approximate the solution to this problem. Okay, so this means you have to rewritten this form, this optimization problem, which is a constant optimization problem, in the form of unconstant problem by using this penalty function. Okay, and this penalty parameter. Okay, so here you know that the solution is very simple. The unconstant problem that is based on problem based on given penalty function, given penalty function, that is you should write here minimize. Okay, what is minimize? Your objective, you know that your objective function plus gamma times your penalty function. So this is standard form. So this is means you write this as minimize. Your objective function is x transpose qx plus gamma. And what is your penalty function? So here already given that what is penalty function. Either here this is given, or you have to calculate what is your penalty function by using this inequality constant, by using gi plus dq. Okay, for that relation you have to obtain. But in this problem already given your penalty function. That's why we write here gamma and norm of this thing. Okay, so that's why this is a reduced problem, and that problem is unconstant optimization problem, and you have to solve that unconstant optimization problem by using that technique. Okay, and here in this case, this is the constant optimization problem. So by penalty method, you reduce your unconstant optimization problem into constant one, and then you're using the unconstant optimization problem technique, and you have to solve that. Okay, so here in this case, you can either solve this. Okay, so if you have to find what is the optimization of that problem is, so now if we try to solve here, so here your problem is complete here. Okay, so now if we solve further, okay, so if we try to solve further here, so here by the first order necessary condition, first order necessary condition. So your optimal solution, that is x gamma, which is the approximate solution. Okay, so x gamma is that that satisfies the derivative equals to zero. Okay, so what is the derivative of that? Means this is your function. The first order condition is if that is your function fx. Okay, the first order derivative is fx prime that equals to zero. So this means if we differentiate this, and this is the x transpose qx, this is a quadratic form, which is x square qx. If we differentiate that equals to 2qx and x at gamma. Okay, plus if you differentiate that, this becomes square and a square. This becomes 4 times of gamma. And here norm of your x gamma square minus 1. And here square, this is 2 of norm x. So this means this of x of gamma. Okay, if you're differentiating first order derivative of that, and for this x gamma, that equals to 0. Okay, so this can be rearranging of that term. So you should get here q of x gamma is equals to 2 gamma, and here 1 minus norm of x gamma square. Okay, and that equals to x gamma, x gamma. Okay, so if we take this value, that is 2 gamma of this value here, this value, and if we take this parameter is suppose lambda gamma. Okay, and here this cube is the matrix, and that matrix is a symmetric matrix. Okay, so this means you write here this form as q of x gamma. Here q is the matrix, and that equals to lambda r x gamma. Okay, so this means this x, if you write here q x gamma, and here x gamma equals to x r, and if you lambda, this lambda is your scalar one. Okay, so this means this x gamma is your eigenvector of that q, because you know that ax equals to lambda x. That means x is the eigenvector of that matrix A. Okay, so here lambda r and lambda are the eigenvalues of this matrix Q. Okay, so this lambda r, this is a scalar. This is scalar. So hence, so x gamma is an eigenvector of matrix Q. Okay, so this is your form, and what is the value of x gamma? X gamma is either your this is your eigenvalues. Okay, so this means here from here your lambda r is equals to 2 gamma 1 minus norm of x square x r. Okay, this is your lambda r. Okay, and that value is this value is scalar one, and that scalar is either less than or equals to the maximum eigenvalue of this matrix lambda. Okay, so this is scalar one, either this is equals to the maximum one, or this should be less than. Okay, so this means you say that what is the value of this 1 minus gamma? So this 1 minus x gamma norm of that square. Okay, so this minus 1, so this equals to lambda over 2 gamma. Okay, and if we take that value is suppose this less or equals to any scalar 1 lambda. Okay, so if this value is for any gamma that is less or equals to gamma, so this means this equals to lambda of 1 minus gamma here. Okay, so if we try to find what is the order of this gamma minus, if we take this value, what is the value of this norm of this square minus 1? So this equals to basically this lambda and 2 are your this lambda by 2 gamma, and this lambda are your scalar one. Okay, so this is basically the order of 1 by gamma here. Okay, So this means your penalty function, basically your penalty function, that is x comma minus 1, okay, that is of order of your in the form of your penalty parameter, that is of order of 1 by gamma k. Okay. So now, in this question, basically, we are interested to write any unconstant optimization problem to constant, any constant optimization problem that is here subject to the constant argument. Constant optimization problem, we rewrite this problem in the form of unconstant optimization problem. Okay, by using penalty function and penalty parameter. Okay, so here penalty function is already given here. Okay, so in some cases this is already given, or you have to find that by using this Cartman Bernoulli penalty function method. Okay, so you should find this one and then write here that P, and your problem is reduces into the unconstant optimization problem, and then you have find that solution. Okay. So now the next method is conjugate gradient algorithm. The next page. Okay. So in this algorithm, conjugate gradient algorithm is summarized as, okay. So here, first step is we set your k, that is initial iteration, that is 0. Okay, and select the initial point. And initial point is x 0. Okay, and then you have to find what is the value of g0, and g0 is basically the gradient of your function at point initial point, that is x0. If this gradient, or we say g0 is equals to 0, अगर ये 0 हो जाए, जिसमें gradient अगर 0 है, this means this is first order necessary condition satisfied, and your point, this point is your uh, optimal solution. Okay, so in that case you have to stop. Okay, अगर ऐसा नहीं है, so else you have to set your d0, and that d0 is the value of g gradient, but in the negative direction, because in positive direction, that is your outward normal. Okay, this is your outward normal, so that's why we have to find the searching for minimization. So we have to go to the inside that direction, so we have to set that d0, that direction is negative of that, okay, minus of that. Then you have to find what is the value of alpha, the step size. That step size is defined as minus of this gk, okay, so that gk, and the direction is dk divided by the dk transpose with the quadratic form of matrix, which function we have to minimize that quadratic form q, and this d of k. Okay, and then next step 4, you have to find xk plus 1. This xk plus 1, that equals to xk, and plus, because here we take the alpha sign with minus signature, okay, this minus sign. That's why we write here plus. If we take alpha k equals to plus sign, then you should define here minus sign. Okay, so this alpha k and dk, alpha k, dk. Then what is next is gk plus 1. So gk plus 1 is equals to gradient of f at point xk plus 1. Okay, so here you have to find So initial one gk, and then here this gk plus 1, that equals to this thing. And if this gk plus 1 that equals to 0, so we have to stop here. Okay. For here k equals to 0, if we're setting here k equals to 0, so we can find alpha 0. This is x1, and here g1. If g1 is 0, then we have to stop. If g1 is not 0, then we have to find what is our beta k. This is our beta k. So this beta k is equals to minus of no, this direction is -1. Okay, so our what is our beta 0? Okay, so beta k. So in that case, beta k is this gk1, g of k plus 1 transpose q dk over dk transpose q dk. Okay, so this is your beta k, and then your seventh step, you have to find the next direction, that is d of k plus 1, and for that next direction you have to use this beta k. So this next direction is equals to minus of g k plus 1 is plus beta k dk. Okay, and then now next step, you have to set your k equals to k plus 1, next iteration, and then you go to step that is 3, and you have to find next one and next one. If this is 0, then you have to stop, otherwise you have to repeat that process until you get that equals to 0 here. Okay, so basically this is the approximate solution. That's why you have to stop at which iteration. This is depending on the what are the order of your accuracy. Okay, so that's why you have to stop your processing. So these are the basic simple algorithm. Okay, so how we can solve our problem by using this technique. Okay, so here if we take suppose okay, so then next पेज ये सारे हैं ही कैलकुलेशन हम यही करना चाहते हैं, चलिए यही लिखते हैं. ओके, सपोज टेक एन एग्जांपल, कंसीडर द क्वाड्रेटिक फंक्शन and that function is f of x1, x2, x3, and that function are suppose 3 by 2 x1 square, 2 x2 square, 2 by 2 x3 square, x1 x3, 2 x2 x3 minus 3x1 minus x3. Okay, suppose any function. Okay, so you have to find the minimizer. You have to find the minimizer, and that minimizer by using the conjugate direction algorithm. Minimizer using the conjugate gradient algorithm, and using your starting point, using the starting point Either this is given or you have to take any arbitrary point, then start. Okay. So this is your arbitrary point. Okay. So now the solution of this problem is we represent this function f. So we can write this function f as in the quadratic form. So we can write this f is equals to 1 by 2 x transpose to x minus x transpose b. Okay, and what is q here? So q is equals to taking half here. This thing, the diagonal entries are 3 and 4 and 3. So this is 3, 4, and 3. What is x1, x2 component is absent here. So 0, x1, x3 is 1. And this is symmetric matrix that has 0. This is 2. This is 1. This is your this form. And x transpose b, what is the linear term is minus 3. So this is 3, x2 is absent. So 3, 0, 1. And b is 301. So this is your you have written this form as equivalent form of that. Okay. So now we have to calculate. First of all, we have to find out what is our gx. Our gx, that gx is gradient of fx. Gradient of fx. If we differentiate this, this is x square of half. This will be qx. So this is qx minus b. Or we differentiate this. This equals to to differentiate it to x1, this becomes this thing. If we differentiate it to x2, so this becomes 2 of x3. If we differentiate it to x3, so this is 2x2 plus 3x3 minus 1. And this is transpose. So this is your gradient of x. So hence, you have to find the initial one, that is your initial point is g0. What is the value of g0? G0 is equals to what is the value of g at initial point, and initial point is 0 here. Okay, so your means this is your g at this at x0. Okay, so g at x0 means you have to putting here 0, 0, 0, x value, that is minus 3, 0, and minus 1. So this value is equals to minus 3, 0, minus 1 transpose. And this value is not equals to 0. If this equals to 0, this means your local mean is this thing. Okay, but here this is non-zero. If this equals to 0, you have to stop. But else you have to set this value is g0 is minus sign of that. Okay, so this implies this is not equals to 0. So this implies you have to set the d0 value, and that is the minus of the d0. So this is d0. So this value is equals to p, 0, and 1. Okay, because the minus sign of that. This is d0. So now you have to find what is the value of next one, alpha 0. What is the value of alpha 0? Alpha 0 is minus d0 over this d0 transpose with q and d0. Okay, and if we you have the value of this d0 and d0, multiply that, so this becomes to multiply here. So this is d0, and so minus 3 and 3, minus 9 and minus 1, minus 9 minus 1, minus 10 and minus sign, that becomes 10 here. This is 10 over if you multiply this t01 with the matrix this thing, so this becomes and then you multiply by 201. So this value is I'm solving, this value is 36. Okay, so 36 means this value is 0.2778. Okay, so this is your step size. The step size is alpha 0. So your next iteration point, that is your x1. So your next iterative point is x1, and that x1 is x0 plus your step size, that is alpha 0. That is alpha 0. Okay, at alpha 0 and b0. Okay, so this after the solving, x0 is 0, 0, 0, and we putting that values. So your value is x1 point is 0.8330 and 0.2778 transpose. Then we have to, if we find x1, okay, so then what is your g1? G1 is gradient of f at this new iterative point. Okay, so here the next iterative state, that is your g1, and g1 you have to find that x1, the gradient at that point is 0 naught. If that equals to 0, then you have to stop there, and if this is not equals to 0, then you proceed. So this equals to, this value is minus that value is 2 0.5556 and 0.6667 transpose, and that is not equal to 0. This is not equal to 0. So that's why if this is not equal to 0, so you should find what is the value of beta 0. Okay, so then you should find beta 0, and that beta 0 is by the formula G1 transpose Q D0 over this D0 transpose Q D0. Okay, and on solving that, value is 0.08025. Okay, so now you go to test D1 value. What is your D1 here? D1 is equals to minus of this G1, so this value is minus of E1 plus beta 0, E0. And here we have this beta 0 value here, E0 value here, and G1 value is this one. Okay. On solving that, we get here this value is 0.4630. Okay, minus 0.5556, 0.5864 transpose. Okay, this value is your D1. Okay, and now you go to this step 3 here. So now your D1 is already known. So for alpha 1, you have to this G1 value, and now you get D1 value here. Okay, so यहाँ से आप अल्फा 1 आप निकाल सकते हो. For step 3, तो यहाँ से आप मूव कर जाओगे step 3. Okay, step 3 में क्या है? That is step 3 is you have to find alpha 1. Alpha 1 is equals to minus of D1, okay, D1 D1 transpose Q D. It is D1 transpose Q D1. Now you have all values are there, so you have to find the value 0.2187. Okay, so now you have to find the next equation, that is x2. X2 is x1 plus alpha 1, that is the direction d1, and your step size is alpha 1. And on putting these values, because x1 is already here, x1 value is this value. Okay, alpha 1 you have calculated this, and what is the d1 direction? The d1 direction is this thing. So this is your direction. On putting these three values in this form, you get this value, and similarly you find x2, x3, x4, and next equation. Okay, so this is a simple procedure how to get these values. आप ऐसे इक्वेशन से करते जाओगे और आपको इसकी वैल्यूज मिलती जाएगी. तो हमने यहाँ पे इनिशियल पॉइंट आपके x0 दिए थे, तो हमने फर्स्ट इक्वेशन पे आपने x1 पॉइंट निकाल लिया, दैट इज x1 पॉइंट, एंड x2 पॉइंट आपने ये निकाल लिया. सिमिलरली आप x3 निकाल लोगे, x4 निकाल लोगे, या फिर जितने इक्वेशंस आपको कहे गए हैं वहाँ आप निकाल लेंगे, या फिर आप आगे एक्सप्रेशन करते जाएंगे. बेसिकली इस प्रॉब्लम में, ये प्रॉब्लम में अगर आप देखें तो थर्ड इटरेशन में इसकी वैल्यूज हमें मिल जाएगी. तो इफ वी गो टू नेक्स्ट पेज एंड रिपीट दिस प्रोसेस, तो ऑन थर्ड पेज और नेक्स्ट पेज द थर्ड स्टेज आर, तो Now, to perform the third iteration, perform the third iteration means we have to find the x3. So we compute g2. G2 is gradient of f at x2. Okay, this value is minus 0.04673 minus 0.1868 is 0.1402. Okay, and then what is beta 1? Beta 1 is equals to B2 transpose Q, and this is D1 divided by D1 transpose Q D1. So this equals to 0.07075. So now you have to obtain D2. D2 is equals to minus of D2 plus beta 1 D1. Okay, so this value is 0.07948. So you calculate it and check it if this is correct or not. Okay, so this is your D2. So now if you find D2, hence what is alpha 2. Okay, तो आपको एक चीज याद रखनी है कि हमारा स्टार्टिंग में जो हम दे रहे थे ग्रेडियंट ऑफ एफ, वहां पे हम D0 को हम सेलेक्ट कर रहे थे D0, बट उसके बाद से हमें D1 और D2 का हमें क्या करना है, फॉर्मूला यूज करना है. ओके, तो हम हमेशा हमें सीधे ग्रेडियंट ऑफ G2 को ही हम D2 डायरेक्शन नहीं ले लेंगे. ओके, फर्स्ट स्टेप में हमें सेम लेना है. ओके, उसके बाद फिर हमें D2 को कैलकुलेट करना है. D1 D2 ये सारे कैलकुलेट करते जाना. ओके, तो अल्फा 2 that is equals to G2 transpose D2 divided by D2 transpose to D2. Okay, if we try to solve, your step size is 0.8231. This is your step size. So your next iteration point, that is x3. So x3 is x2, and in case of minus, but here where our is taking minus sign, that's why this is plus of step size in direction of this. Okay, so if we putting all these values, three values, so we get here 1.000 and 0.000, and here this is 0.000. So this is your x3 point 100. Okay, so note that at this point, that is G3. G3 is gradient of at f x3. If we try to putting that x3 in that equation, that is 0. Okay, so this is as expected because f is quadratic. आपको मालूम है क्वाड्रेटिक डायरेक्शन मेथड में if there are n variables, so we can find our solution in n steps. Okay, so in that case there are only 3 variables, so here we find optimal solution at third step. Okay, so that's why we write here as expected, because f is quadratic function of 3 variables. Quadratic function of 3 variables. Okay, so your x star, that point is x3. x3 means that is 1 0 0. Okay, so this is so answer. तो इस तरह से आप कर सकते हो. Okay, तो आज इतना ही रहने देते हैं, मेरे ख्याल से इतना काफ़ी. तो इतना कर लिया. अब कुछ क्वेश्चन और बचे हैं आपके, उसको हम नेक्स्ट वीक में हम कोशिश करेंगे कि इसको हम नेक्स्ट वीक में इसको हम करा दें। तो आज के लिए इतना ही रखते हैं, और भी कोई प्रॉब्लम होगी तो आप डिस्कस कर लेंगे हमसे। नेक्स्ट वीक में हम लीनियर ऑप्टिमाइजेशन और जो कुछ एप्लीकेशन हैं वो हम करा देंगे। और आपकी एग्जामिनेशन जो है वो कहीं आफ्टर 20 जुलाई आपकी एग्जामिनेशन स्टार्ट होंगे सेकेंड सेमेस्टर की। तब तक आप असाइनमेंट आप सबमिट करें और अपनी एग्जामिनेशन की भी तैयारी आप धीरे धीरे करते रहें, ठीक है।